you hear that scientists made a significant discovery, you might think, oh, they found something important. Be careful, because they might be talking about statistical significance. And statistical significance is very different than significance in the sense that most people think significance is. So statistical significance does not mean important, it does not mean large, it does not even mean real. Statistical significance just means that a finding, in oversimplified terms, is unlikely to be due to chance alone, with unlikely being determined by an arbitrary cutoff value. Often this value is the p-value. And I'm not going to go into the mathematics of how the p-value is calculated and all of these things, but basically the lower the p-value, the more unlikely it is to be a chance alone finding. It is more complicated than this, but it's often described as a p-value of less than 0.05 would mean that there is a less than 1 in 20 chance that the finding is just due to random chance. But the p-value is going to depend on a lot of different things, including how many people or how many samples there are in the study. And so you could have a large effect in a small study that is then considered non-significant because you don't have enough statistical power, you don't have enough samples, and that exact same effect size in a large study is then going to be considered significant because now you have the statistical power to show that, yeah, there does seem to be a kind of difference between this group and this group. And so there's kind of, you got to choose a cutoff line. And so the cutoff line is often chosen to be a p-value of 0.05. And so you say, okay, well, if you've got a value under 0.05, so maybe 0.04999, hey, we found something significant. And if it's 0.051, oh, not significant. And so we can ignore that and just report this one. And the more things that you test, the more likely you are to, by chance alone, find some of those that are considered significant because they're under that threshold value. And so this is like multiple comparisons and multiple tests, multiple hypotheses and things. People test a large number of things, and then they choose the ones that are significant and report those. And so that is called cherry picking. This is one type of p-hacking. And so p-hacking is where people kind of use these various strategies in order to find data that is under the threshold so that they can report it as a significant finding. When people do multiple comparisons, they need to make sure that when they're doing their statistical analysis, they correct for that. And so there are various sorts of statistical things that can be done in order to kind of make the conditions more strict. If you are doing multiple comparisons, in order to say something significant, then you need to be kind of stricter than if you were just doing a single comparison. But again, just having a statistically significant finding doesn't mean that something actually is a real finding. And even if it is a real finding, it doesn't mean that it's actually meaningful or replicable. People also do things like splitting up data in like arbitrarily. So you've got this continuous data. So maybe it's height of people, and then you chop it off here and say, okay, these people are short and these people are tall. If I cut it off here, there's a statistical difference between them. And if I cut it off here, there's not. So let's cut it off here, or let's cut it off here, depending on what I want to say with my value, with my data. There are also people can do things like they look at the data midway through their experiment, and then if things are like the p-value is under the threshold, they're like, okay, let's stop here. And then if it's not, they're like, okay, let's just collect more samples, because the more samples I have, the kind of smaller the effect can be, and I can still have statistical significance. Another thing is leaving out outliers that aren't justified to leave out, which can skew the data. Another thing that kind of goes along with the multiple testing is when you test a lot of different things and then you find something that is significant, and then you kind of say, okay, well, I knew I was going to find that one from the very beginning. And so you kind of hypothesize after results are known. And it might sound angelic, but it really is not. Because when you apply statistical tests that were designed for kind of going in there with the hypothesis that something is true, to experiments where that was not how the experiment was designed, instead you kind of like found this and then drew a bullseye around that dart in the wall, well, now those tests are not going to be valid. And so you need to set up an additional experiment where now you use that as your hypothesis going in. And so when scientists go on like fishing expeditions, and so this is kind of used as a pejorative term, but it can be important to have exploratory studies where scientists go and they try to find hypotheses, but they're finding hypotheses that then they need to follow up with future tests. They can't say, okay, well, we found this possible connection, and that connection might just be due to chance alone. It could just be due to like fitting to random noise and all these things depending on the sample population and all of these factors. And so that's why then you need to set up another experiment with this new thing that you discovered as your hypothesis, and then follow up to see if that really is a real finding. And the best way to really follow these up is often with a different type of experiment. So maybe some orthogonal strategy, some orthogonal technique that kind of goes about answering the question of the hypothesis by collecting a different type of data, say, or some other confirmatory factor. And so maybe you do a screen where you're using CRISPR or something to knock out different genes and see which of these has an effect on allowing the cells to survive in the presence of a drug, or that makes them like die off in the presence of a drug. If you find something, then you're going to want to follow up with additional studies in order to confirm that. And so often this is done, but sometimes this is not done. And so you want to be really careful, especially in those early stages when people are reporting that things are significant findings without really thinking about what significant means. And so the p-value is very problematic for a variety of different factors. The various statistical tests can be problematic. People often, what they do instead of the p-value is now they'll kind of report the confidence interval and say, okay, it's 95% likely that the true value is between here and here, that sort of thing. And so you get more of a range. So there are better ways to report statistics than just like the p-value. But often what people use is the p-value. And they'll say like, okay, so if it's under this threshold, we'll say it's significant. And if it's over that threshold, we say it's not significant. And maybe then we'll indicate with an asterisk that something is significant, or we'll say like NS, like not significant, if there is no significant difference. But again, significant does not mean important. It does not mean meaningful. It does not tell you about the size of the effect, and it doesn't tell you about like whether that effect is actually meaningful, let alone real. And so say you have a real finding, that real finding, you find that there really is a difference between these two groups, maybe one group that took a drug and one that didn't take a drug, and maybe you find that the group that took a drug, their hair grew 0.1 centimeters longer over the course of 5 years. Maybe that's statistically significant, but is that important? Is that meaningful? Probably not. So you want to be really careful when something is said to be significant. Ask yourself, are they talking about statistical significance, or are they talking about like meaningful significance? And so if you use the word significant, be very careful with how you use the word significant. And if you're not talking about statistical significance, then I recommend you use a different word. And if you're talking about statistical significance, please add that word statistical. And so I've seen a lot of people get confused by this, and don't let yourself be fooled, and try to prevent yourself from fooling other people. Don't engage in those p-hacking strategies. A lot of times scientists don't even realize that these are statistical mistakes that they might be making during their experiments. So it's important to keep these in mind. And I highly encourage you to check out some of this recommended reading so that you avoid making these mistakes. And then for people who are kind of trying to interpret results, that you be really careful when you're dealing with statistical significance. If you want to learn more about these topics, I'll recommend some books and things, because again, I am not a statistician, but I do know that this is a very common problem.